lesson. You guys need to let me know when class is over, because now I don't have my handy dandy schedule in front of me. So I'm not 100% sure. I think what it's 11:25 we're done. There we go. Thank you, Gabe. So I'm going to go ahead and get started. Let me pull up the book. So it is this one. We all see my screen? We all see the book? Does it say lines of symmetry or does it say something else? I can't see my yellow bar, so I'm not. Oh, you know what it is? I have two screens and I should have just checked my other one because I can see, I can see what I'm talking about. All right, so investigating symmetry. We all know what symmetry is. If I take something and I fold it over itself, it matches up perfectly, okay? So we have here the vocabulary that we already did. Figure has symmetry if a rigid motion exists that maps the figure onto itself. So remember, rigid motion is the translation, rotation, and reflection. Doesn't change the size, right? If you change the size and then try to reflect it, it's not going to match up perfectly, okay? As you can see here, the triangle, which is what I drew for you guys, the book, see they have a little crescent moon here. I thought maybe I should try that, and then I remembered my drawing skills and thought better of it. So I went with the triangle, right? If you cut the triangle in half, you get the two halves. It is symmetrical. It would have one line of symmetry, right? So the line of symmetry is pretty much the part where you cut it so that you can get the even halves. So for example, in this first figure, you can have 1, 2, and probably 3 and 4 lines, right? If you cut it diagonally. The problem with rectangles is it's a little weird because sometimes they don't always match up. So I am very hesitant with the diagonal cutting, but a square would work, right? If you had a square, a perfect square, and you cut it diagonally, it would line up perfectly. This triangle, does this triangle have any symmetry?
No.
No, right? It's a really weird shape. No symmetry is happening there. And this L shape, does this L shape, it's not really an L. Does this shape have any symmetry? You can give me a thumbs up if it does. I think you even, the guys have like now, but you have a green check or something. What is this laughing happening over there? I can see you guys. Nice to see you. Please try to refrain from the chat because when I'm sharing my screen, I can't see it very easily. But I can draw here. Symmetry, yes? So it can technically have one line of symmetry. That's if these are the same length, okay? Oh no, I don't want that following me. This is why I don't annotate with this thing. There we go. All right, the next thing is rotational symmetry. So rotational symmetry is kind of pretty much what it sounds like. If I, instead of reflecting my shape, I'm turning it. So if I turn my shape a certain number of degrees, it's going to line up to its original way. So we have here the little star, right? So it says if I turn the star 72 degrees, I'll still look like a star, okay? A figure has rotational symmetry if the rotation maps the figure onto itself. The angle of rotational symmetry, which is greater than 0 degrees but less than or equal to 180, is the smallest angle that maps onto itself, okay? So for example, the star has 5 points, yes? You see that. what you do is you take 360 degrees, that's the full circle, and you divide it by 5, by however many sides the shape has, okay? That gives me 72 degrees. So the star coincides with itself. The angles of rotation for the star are 72, 144, 216, and 288. That goes every time you turn, you're adding 72. If this is my starting point, when I go here, that's plus 72. When I go over here, that's another plus 72. Plus 72, plus 72, plus 72. So you see how that works? So that's why there's all those different sizes. But the angle of rotational symmetry is the smallest one, which is that 72. Okay, does that make sense? Yes? This stuff isn't so bad. I'm not gonna go through those shapes, that's just turning it around. And then this is where your homework is. So your homework is just 1 through 8. Pretty simple, right? So the first 3, draw all lines of symmetry for the figure. You know, you cut it up as many times as you can to see how many you get, and then you write how many lines of symmetry there are for all of them. Then you're going to do almost the same thing, but in this case, the angle of rotation. Okay, and the last one is determine if it has line and or rotational symmetry. Okay, if it has none, you just put no. There's no symmetry to it. Okay. Any questions on this part?
What page is that?
This one in the online book is page 94. I don't have my book next to me, so I don't know. 106. It's 106 in the actual book. So if Vale wants to get the page out of her textbook, 106. I think she can hear me. I would think she's one. Oh, there she is. See, so you don't have to lug around your textbook. Just rip out page 106. That's all you need. All 8 questions are on that one page. We're good with this? This part isn't so bad. This whole section isn't so bad. Okay. The reason I'm trying to get through 3 lessons today, which I don't think I will. I got through like 1.5 with second period. But if we can get through the other 1.5, I'm pretty sure that just leaves maybe on Monday 1/2 of a lesson. And then that gives us basically a whole week to review for your test. And I think we all kind of want a whole week to review, right? I think that's in everyone's favor.
Wait, what did you say?
That we're almost done with all the lessons that we need for our test. So I'm trying to finish up the last ones. That's why I'm trying to combine as many as I can into one day. And because the symmetry and what we're going to talk about right now, there's not really much to do with it. We can agree, right? It's just looking at the shapes and saying, okay, I can cut it this many times, or 360 divided by however many sides there are. You get what I'm saying? So I'm trying to get through it because remember, our deadline for our test is September 30th. That's the last day we have to take the test. And I want to give you guys at least 2 class periods to do it. It's only 12 questions. I don't think it'll take more than a class period, but I know that sometimes we get a little nervous. So I want to give you guys the full, at least 2 days to do it. If we finish up these lessons ASAP, so hopefully by Monday or Tuesday next week, that means we then spend the rest of the week until next week, the following, reviewing. So basically on the 28th is when I'm trying to get us so that we can start the test. 29th is kind of pushing it because I don't really want us to hit that the 30th, but my goal is to have us start taking the test on the 28th. Okay, yes? What is Matt saying, Gabe? Does he have a question? He's talking bad about me? Let's see, let's see. All right, so I'm gonna go ahead and stop sharing this one so I can pull up the next section of the textbook. But your homework is only on that section. There's no homework in the other sections that we're gonna talk about right now, okay? So our next topic is on, where is it? There it is. Sequences of transformations. So sequence means what? Like more than one, right? We have a sequence of things. It's usually like a pattern or a trend or something like that. So we're pretty much looking at what happens when you apply more than one transformation to a figure. So this section talks about, the first part is combining rotations or reflections. This whole blurb here at the top tells you to use a geometry software, and I know there's one that they recommend, and for the life of me, I cannot remember what it's called. It's like Geo something, but you can Google it online and find something that you could, if you had the desire to see it, you can find something online and test it out yourself. But the first main section is combining rigid transformations. So remember that rigid transformations don't change its size, okay? We're just looking at the transformations of reflection, rotation, and slide, okay? So we have here, draw the image of ABC after the given combination of transformations. So the first thing is a reflection over line L, and then a translation along the vector. So there's my vector up here. Here's my original, my pre-image, right? Step one is draw the image of triangle ABC after a reflection. So when they give it to you with words, you want to do it in the order that they tell you, right? Reflection, then translation. Don't try and do the translation first and then reflect it, okay? Always do it in the way they describe, all right? So the first thing was to do the reflection. So we see our ABC gets flipped over line L to triangle A prime, B prime, and C prime, okay? Then we translate it along the line. So the line is telling me to point this way. So we're kind of just gonna grab the shape and push it over. Now, when it comes to something like that, where they just tell you along the vector and they just show you the picture of the vector, you don't have to be accurate, okay? They're not giving you an exact number. There's not giving you any points to work with. You just kind of have to follow where the line points and say, yeah, this looks good, right? You can even see it in theirs, how it kind of like overlaps line L, because they just kind of like shoved it over. So it's not going to be accurate. But if you can see, I can zoom in. What do we have there? Two lines. So this would be A double prime, B double prime, C double prime, okay? It's not a secret to the names. It's just prime, then you have two of them, so double, okay? That would be it. That's multiple transformations in with a triangle. The next one, this one is fun. Look at that. Look at all the colors. So we start off with our blue pre-image triangle. First thing is a rotation around point P of 180 degrees. So here's point P. I'm rotating it all the way around. Remember, it's going to be the complete opposite. So that gives me my A prime, B prime, C prime triangle. Then a translation along the vector. So you can see the vector down here, how it goes up just a little bit. So when they slid it over, they moved it up over one, okay? You can actually see it points to that one part. Even though it's not like where the arrow is, you get what I'm saying? It's telling you, stop on this second line. So that's kind of how they guided it, okay? So we have here A double prime, B double prime, C double prime. So this is after I've slid it along the vector. Then I'm going to reflect it across line L. So I reflect it, and there it is. A triple prime, B triple prime, C triple prime. Every translation you do, you add a little line, okay? Make sense? Why not?
Wait. I have some questions.
What are
Okay.
your questions, Katie?
I heard someone say, "Oh, that was mean." But anyways, okay. So when you rotate it
It's just like I'm there. What
when you rotate it 180 degrees, how come you don't keep it on the same point? Like,
do you mean?
how come you move? Can I annotate?
I don't know. I don't really
No,
like.
I know I can. It's just like, can I? Like, may I, you know?
Yeah, you can. If it
Okay,
works
so
for you.
basically, you know how this point's right here? How
Uh-huh.
come it goes to here instead of staying right there when
Because
it
it's,
flips?
so it's rotating. Let me see if I change my color. It's rotating around this point here.
Mm-hmm.
So if I'm rotating it 180, I want it to be the opposite.
Oh,
So
okay.
like this point here becomes my new 0, 0, right? So this would be a -1. So this would be a +1.
Okay.
You get what I'm saying?
Yeah. Wait, point equals, okay.
When you're
Okay.
rotating it around a specific point, think of it that way. That new point is your 0, 0. Okay. And then go from there on the rotations.
And then, okay, so then when they're going from here to here, how come they slide it up a point, or is that just because the book is
The
being
vector down here.
Oh, okay.
Yeah, you have to look and you're going to find somewhere on that graph, they're going to tell you where that vector is and where it's pointing. On your test, I don't think there's one like that. So we're good. But it would be like that. You would just follow it. And this one ends on the second one up from where it started. So I think that's why they go, that C gets lifted up 1 point.
Okay. And then, wait. Oh, okay. So then when you're like going along a vector, would you just match it like C to C, you know?
Yeah,
Or
so you're not changing the orientation. You're not rotating it. You're not doing anything. You're just sliding it around. So if my pencil's facing up this way and I just slide it, it stays the same way, right?
yes. Okay. So wait, can you scroll up just a little bit to the same page? It's the same page.
Yeah, why isn't that?
So then for, oh wait, let me clear.
I got it.
Okay, there. So then for, wait, where is it? So then for here, is it B to B?
Yeah, so they, once again, they follow the vector.
Mm-hmm. Yeah.
But if you see, they do it with all of them. B to B,
Yeah.
C and C, A and A. They're all going in the same trend as the vector line that they give you.
So then if this one goes up a space though, how come it's going down here?
It's not really going down. So you see, look, it looks like it's going down because we're originally following this line. But if you look here, look at where A prime actually is. A double prime is up 1.
No, what? Wait, where's it up 1? It's on the same line.
It's not on the same line. Let me pick a different color. Here.
Oh.
You see?
Okay.
It really goes up, but because this line L is there, you think it's going down, but it's not. It's just, it's a different line.
Okay, thank you.
Okay? We clear up all the confusion we might have had?
Yes.
Anyone else? We're all good? All right, I'm moving on. Combining non-rigid transformations. So we haven't really done a lot of non-rigid transformations. I'm going to do one after we go through this, so don't worry too much. But we have here, draw the image of the figure in the plane after the given combination of transformations. So I prefer seeing my stuff this way. Why isn't it letting me? There we go. I prefer this way. Why? Because they give me my coordinate notation. So it doesn't matter if I don't remember what my transformations are. Like if I don't remember this one right here, go back to my annotate. If I don't remember what this transformation is, I don't really need to worry. I don't need to worry because they're telling me, switch your sign for X. So I can just kind of forget it. So basically what you're doing is you're at your starting point. Then you're doing this transformation. Then you're doing this transformation. And then you're doing this transformation. Okay, so it's in an order, right? Just like the other one was do this, then that. Instead of saying then, they put it with the coordinates, which I like better because I don't need to worry too much and I can be a little bit more accurate even. So I have here my original, which is the blue. Then I am going to transform it by a dilation by a factor of 3/2. Remember, 3/2 is really 1 1/2, right? It's an improper fraction. If I change it into a proper fraction, it's 1 1/2. So that's why my first image, A prime, B prime, C prime, D prime, is larger than my original, okay? Then I'm gonna go ahead and do the second transformation, which happens to be a reflection across the Y. So my B, which was at what, 3, 6, now gets flipped over to -3, 6, C to -9, 6, and so on and so forth. And that becomes A double prime, B double prime, C double prime, and D double prime. So far, so good? Yes? And then the last transformation is just a slide of 1 to the right and down 2. So like I have C here, goes over to -8 and down 2. Are we good? Kind of see. It's kind of all the transformations in one, but I like this better because they actually tell me. So here we have something now also called a stretch, which we didn't really talk about stretch, and it bothers me that they didn't do a whole section on just dilation and stretch and all that stuff, because they gave translation, they gave rotation, and they gave reflection, all their own section, but they kind of forgot about the dilation and the stretch and all that stuff. So it's kind of annoying, but we'll do an example. So when you have a stretch, it's only going to be multiplying one of your X or Y, right? So for example, this is a stretch of the X. So you see this A prime, B prime, and C prime is stretching of the X. You see that it's stretched out, it's longer. Like if you take a rubber band and you stretch it, it goes from being a nice little rubber band to really thin. So it's the same kind of thing, you're stretching it out. And then we have another dilation by 1/2, but it's not just that, because I have here, wait, I can annotate. I should have figured this out during second period. It would have made my life much easier. I have a -1/2. So that's actually a double whammy because that's 2 transformations in this one coordinate rotation. That's the dilation and a reflection, okay? But again, when they give it to me as the coordinate notation, I don't really need to remember that. I need to notice that negative sign, but I don't need to remember, oh, I also have to reflect it. I just take my X and my Y and I apply the numbers, okay? So it's a little less stressful, I think, because as long as I know what I'm doing, it doesn't matter if they throw in 5 negatives, which they wouldn't do because you only have 2 numbers. But you guys get my point. It doesn't matter what they give you because they're giving me this coordinate notation, which helps out my entire life because I don't need to think too much. Okay. Predicting, yes.
Okay, sorry, but wait, can you go back?
Yes.
Okay, so wait, can you go up a little? How'd you, wait, how come you called that a dilation when it's getting bigger? From A to A prime, it's getting bigger.
Dilation getting bigger?
So-
Dilation is getting smaller though.
So this is what this book does, and I noticed it. They don't use dilation or reduction. They just call anything that's changing the size a dilation. They just say a dilation by 3, a dilation by 1/2. You can see here, first transformation is a dilation by a factor of 3/2. Yes? Then when I go down here, the second transformation is a dilation by a factor of 1/2. But they're not going to be the same.
Mhm.
So they just call any change in the size a dilation.
Okay,
Okay. So I'm going to keep it that way because if your book is using it, then most likely the test. But once again, we'll have a study guide for the test. Don't worry too much about that.
Can I use the
Yes.
bathroom?
Yes, go.
and okay, so also wait, it's dilation and reduction, and then what is it? Stretch and compress?
Yeah, it would be stretch and compression, but most likely they're just going to be like a stretch, and that's it. They're probably not going to go into it, but yes, it would be a compression or a stretch.
What's the difference between all 4?
So the dilation and the reduction, isn't dilation thinking of like your pupils? When your pupils dilate, they get bigger.
Yeah.
So
Oh, wait.
dilation.
Is it?
Dilation is getting bigger, reduction is getting smaller. Stretch is when you see it here. It gets stretched
Yeah.
out. And a compression is when you scrunch it up together. Okay?
Okay.
Squishing. It's squishing, basically. You're either squishing it horizontally or you're squishing it vertically.
Okay.
Okay?
Thank you.
Mhm. So the next one is predicting the effect of transformations. This one isn't so bad. You're not actually doing the transformations. There's only one that you actually need to pay attention to. But most of the time when you see these questions, it's usually going to be starting in this quadrant, where will you end up? That's the kind of question this is. They're not asking you to perform these transformations. They're just asking for where is your final image going to be? Okay, but you do need to do, see how they say the vector? You do need to do that translation first. Why? Because if I have a translation, it can end up over here, it could end up over here, it could end up over here, it could end up in any quadrant, right? So I need to check, that's the only one I need to check for. Other than that, I don't care, right? So this is a transformation of x moving 2 to the left, because it's -2, and 3 up. Yes, right? We're all good? So that means I'm taking my m, and I only need to pay attention to one point, really, right? So 1, 2, and then 1, 2, 3. So my m ends up here. That means all my other points are ending up in the same quadrant, right? So luckily for me, I didn't move here. Now I can pay attention to the other transformations. So it says reflected across the y-axis, meaning it's going to flip over to this quadrant, and then reflected across the x-axis. So now it's flipping over down here. So which quadrant did I end up in?
4?
4. Exactly. Remember that this is 1, 2. I have a mouse. Why am I doing this to myself? I think the mouse might be worse. I changed my mind.
I have a pen. Do you want me to? Okay.
No, I got it. 1, 2, 3, 4. Remember, it's in the C. I'm going to switch over to the iPad, which you guys are going to be impressed. Promise you. So this is just temporary. But we see what I'm talking about. These kinds of questions, they're really asking for what quadrant do you end up in. So if I had this over here, I reflected over here and reflected down there, I'm ending up in the 4th quadrant. Okay. Any questions on that one? Nope. And that's the end of that section. So I'm going to stop sharing. I'm going to share on my other screen because I am fancy like this. There we go. We all see my screen, yes? All right. I'm assuming we see it because I can see it. So we're going to just do a simple, look at that, simple graphing dilation problem with my oh so beautiful graph. I need this on my whiteboard so that way we can have beautifully drawn graphs. Because wait till you see the triangle. Wait till you see the triangle. All right, I'm just kind of getting this together. I'm skipping 1 so it's bigger for you guys, but it's going to be 1, 2, 3, 4, 2, 3, 4, 5, 6, whatever. So I'm going to use the points, and I need another page. I'm going to use the points 4, 2, 0, 0, and let's do, I don't know, 2, 2. So I'm going to come over here and I'm going to graph it. So I have 0, 0. That's not a good color to use. 0, 0. 4, 2. And 2, 2. So now, there we go. That is a good looking triangle. So I'm going to go ahead and my transformation is going to be x, y becomes, what do I want? 1/2 x, 1/2 y. We'll keep it simple. Okay. So once again, I just take all of my points and apply the transformation. So 1/2 times 4, 1/2 times 1, or 2/1. So what is going to be 4 times 1/2?
2.
2. And 1/2 divided by, or 2 divided by 1/2?
1.
1. And I'm going to do 0, 0, which is just going to be 0, 0. I'm not going to waste too much time doing that. We all know that anything times 0 is just 0. And then we have 1/2 times 2, 1/2 times 2, which we already figured out is 1, so it's 1, 1. Now I'm going to go back to my picture. What do we have? 2, 1, 0, 0, and 1, 1. So as we can see, we now have a little bitty triangle. Okay, so it's the same. What?
Was this a compression? I'm confused.
This is one of the dilations because it's shrunk.
Okay.
You see, it's the same shape, it's the same triangle. It's
Mhm.
not stretched, but it's smaller. We all see that? Even look, I have fancy new technology. So now they actually look like triangles. They're not lumpy.
Okay.
Okay? But that's basically because we didn't really do much dilation. I just wanted to give you guys one example. It's simple when they give it to you like this because it's just multiplying and dividing, right? It's nothing extra that we have to do. It's nothing extra that we have to learn. It's stuff we already know. Okay? It's just we haven't really been able to apply it. And then we have a few more minutes. So I'm going to go ahead and switch back to the book just so we can start looking at the next section. So remember, you only have one homework, which is page 106, 1 through 8, or whatever the online one was. I don't remember right now. But now we're going to talk about proving figures are congruent using rigid motions. So what does congruent mean?
Equal.
Right, they're the same. They're equal. They look the same. So this whole thing talks about using trace paper. We're not going to even acknowledge that because we're not going to do that. Because once again, just like a compass and just like a protractor, the test is not going to tell you, put some trace paper on the monitor and draw the figure. Okay? Not only that, but how would they even grade it and check it if it's on a paper? So we're not worried too much about trace paper stuff. But here we go, determining if figures are congruent. So use the definition of congruence to decide whether the two figures are congruent. Okay, so they're telling you the two figures appear to be the same size and shape. So look for the rigid motion that will map one to the other. Okay, very simple. They're telling you these two kind of look like they would match up, but what can be done to prove that they do line up? So for this first example, what would it be?
A reflection over the y-axis.
Oh, it does. Did you read it, Kaylee? Did you cheat?
Okay, a reflection.
I think Kaylee cheated. I can't block out the whole book.
What?
There. Now you can't cheat. Now you can't read the sign.
I was saying a reflection over the
She
y-axis.
wasn't cheating.
Oh, yeah, but you know what? It shows the answer there on the side, so I have to be careful.
I didn't even see that. I was confused.
It is a reflection over the y, right? Here's my y-axis. Here's my image. It's flipped over. They are congruent. Okay. This one. These look to be the same shape, but what transformation gets me from this triangle to this triangle?
A 180 degrees rotation?
No.
90 degrees.
I heard, wait, who said it?
Elena.
Okay, yes, Elena is right. It is a rotation of 90 degrees. See, this thing is so delayed that when someone speaks, it's supposed to pop up higher, but it's so delayed, I didn't know who said it. But yes, it is a 90-degree rotation. Remember, 90 and 270 end up with your shape on its side. Okay, it is going what? Counterclockwise. So it would be 90 degrees. Is that a rigid transformation?
Yes, but wait, how do you know which one's the image and the pre-image if it doesn't have the tick marks?
Oh, well, in the...
I thought YXC was the first one.
No, you should always go by the alphabet. So you can map ABC to XYZ. So you always want to go with the alphabet way. If you went the other way, you could still say it was a 90-degree, but it was be clockwise instead of counter. Okay. I know you guys have like 3 minutes left. Oh, you know what? I think we did pretty much up until, but I just want to do this one quickly because this is the last one I stopped on the second period. So this one is with a sequence of rigid motions, so more than one. So how do I go from triangle ABC to triangle PQR? What do I do?
Could it be two reflections?
Rotation of 180.
A
Ooh,
rotation of 180 is 1, right? Because my A is now where my P is and everything is backwards. But then
Or
what's my,
a reflection over the Y and then over the X.
That's what I said.
no,
Or no, I mean,
we got the rotation.
what about a reflection over the X and then the Y though?
Y and then the
No, but then
Oh, yeah,
if
you're
it's
right,
going
you're
like
right.
that, then it's going like that. How come it couldn't be two? Oh, Alexa's been here too. How come it can't be two reflections?
So my C is at what? -2, -2, right?
It's a slide.
There is a slight slide of 1 only on my X.
Wait. How
Hold
come? I'm confused now.
It can't be a reflection because the reflection would map it exactly there.
How
Right?
come? Wait.
Because look, it starts here and then this one's all
One
the way
comma
here.
two. Oh, okay. Gotcha.
So then you would have to do a rotation of 180 and then a slide of just 1. And that's it.
Wait, wouldn't it be a half?
No, because this is by twos. 2, 4, 6, 8.
Oh,
So half of it is 1.
one.
Okay.
I get
And
it.
we're good. So remember your homework. If you're using the book, 106. If you're using the online, I have no idea. 96? Is that what it was, Kaylee?
I think it was 94 because
not
that's
bad.
what I wrote down.
It was 90 something. 96 or 94. But